Hi, my name is Xinyang Liu. I'm presenting my final report for the STATS 610 Bayesian statistics, and the title of my final project is Application of Bayesian Methods for Quantitative Trait Loci Mapping. So here is the overview of my presentation. First, I'm going to introduce the data structure and some concepts of the single marker analysis. Then we will extend the single marker to the multi-gene model. Also, I will introduce the variable selections and the core of this project, which is the Bayesian analysis, and followed by the algorithms. And finally, I will give the results of my report. So what are genotypes? Mouse carries two homologous chromosomes, one inherited from each parent, that code for the same trait but may carry different genetic information. And the genetic information on the two chromosomes combined together becomes to the genotype at certain marker. And in our dataset, a total of 107 markers were genotyped across the 19 autosomes of 900 F2 female mice. So these genotypes are the independent variables in our regression model, and the phenotype is just the trait of interest. In this project, we chose the adjusted insulin-like growth factor 1 levels as the phenotype. So this is the dependent variable in our regression model, which is Y. So next, I'll introduce the single marker analysis. Suppose there is one marker associated with the trait, and three possible genotypes at this marker are big W, big W, big W, small w, and small w, small w. And the observed phenotype Y then can be expressed by the following additive effects model. So mu here is just the population mean for the trait Y, and for the big W, there is a additive effect of A, and for the small w, there is a negative effect of A. And for the big W, small w, the effect is another parameter. We define it as D. So since we have defined the single marker model, now we can extend it to the multivariable model here, because in the real data, we are not just interested in the single marker. We need to include all the markers together in one model to see which ones are associated with the phenotype, the trait. And so mu is the same as before, and now we use X and Z to denote the genotype indicator for the homozygotes and heterozygotes respectively. The reason why we use these definitions here is just for the simplicity of the regression, and the same A and D are the additive effects and the dominance effects. And L here is the number of markers included in the model, which is 107 for our dataset. And the error epsilon I is the normal distributed with mean 0 and the variance sigma square. Since we aim to identify the loci associated with the trait from lots of candidate markers, it becomes a variable selection problem. In other words, we believe that many of the regression coefficients are potentially equal to 0. Then we simply come up with a prior distribution that reflects this possibility. This can be accomplished by specifying that each regression coefficient has some non-zero probability of being exactly 0. With this parameterization, our regression equation can be expressed as follows. So we just add a new parameter tj here in the equation. The tj's indicate which regression coefficients are non-zero. So now we come to the Bayesian analysis part. First, we can derive the likelihood function under the assumption of normal distribution for the errors. The likelihood function for y is also normal distribution. And then we write the prior distribution. The genetic effects A and D is a multivariate normal prior distribution, which is conjugate. And the variance, sigma squares, is assigned a semi-conjugate prior distribution of inverse gamma. So with likelihood function and the prior distribution, we can derive the posterior distribution using the Bayesian theorem. And we also know that the 4 conditional distributions for the parameters have the closed forms. And then we use the Gibbs sampling to derive the posterior distribution of the parameters. And here is the algorithm. First, we set t to the ts, and the second step is for j in 1 to p in random order. We replace tj with a sample from the marginal probability distribution of tj given other parameters. Then we get the new value of t, and then we can sample a new value of sigma squares from its full conditional distribution. And similarly, we can also sample a new value from a new value of beta from its full conditional distribution, and then we repeat these procedures till the convergence. Now we come to the results part. As we can see, the plot above shows the posterior probabilities that each coefficient is non-zero. For the first column, it has the probability of 1 because it represents the population mean, which is the intercept term in the regression model. So it must be included in the model with a probability of 1. And then we use the threshold of 0.5 to identify significant markers. Now we identify 2 markers, one on the chromosome 6 and the other on chromosome 10. And we can see the plot below. The green arrows indicate the corresponding positions of these 2 markers on the chromosome. And this means the genotypes at these 2 markers are associated with the phenotype. So finally, here is the table for the posterior means and 95% confidence intervals for the parameters, including population mean, and the additive effects and the dominance effects at the 2 markers we have identified before, and their values are listed below. So that's pretty much it. Thank you.